Welcome to The Deep Dive. Today we're diving deep into some source material about, well, a phase of matter that genuinely sounds like science fiction, but it's absolutely real: time crystals.
It really does sound like something straight out of a novel, doesn't it?
Totally.
Yep.
We've got a detailed report here exploring what they are, how they work, and some incredibly exciting potential applications, especially, in the quantum realm.
Yeah, the possibilities are pretty staggering when you start looking into it.
So our mission today is to unpack this complex topic for you, pull out the key ideas from these sources, highlight the very latest breakthroughs, and try to figure out what this strange new thing could mean.
For technology, for energy.
Exactly. And even just our basic understanding of time itself. Get ready, because this is one of those topics that might just shift how you see the universe a little. Okay, let's unpack this.
All right, so the fundamental question first. What is a time crystal?
Right, let's start there.
The core idea, as the research points out, is that it's a phase of matter that repeats in time. You know, the way ordinary crystals repeat in space.
Ah, like the analogy I saw, which I loved. You picture a regular crystal, like a snowflake.
Perfect example.
It has that beautiful repeating pattern in its structure, its atoms arranged in a regular grid that repeats spatially.
Precisely. Now, with a time crystal, you're looking at a system whose state, its whole configuration, it repeats at regular intervals, but in time, not space.
Okay, repeating in time. But the truly, mind-bending characteristic the research highlights is that they seem to oscillate indefinitely without using or dissipating energy. That just feels wrong somehow.
It does feel counterintuitive, absolutely.
Yeah.
Most systems we know tend towards equilibrium, right? They find their lowest energy state, eventually stop moving, lose their structure.
Yeah, things run down.
Entropy.
But these time crystals, they just keep going. They stay
Like
elusive.
they don't settle down. That's the crucial distinction. They exist in what's called a non-equilibrium state. They maintain their dynamic oscillating pattern perpetually without the continuous energy input you'd normally need to keep something going against friction or loss.
It's a very, very different way for matter to behave.
Fundamentally different.
Okay, so repeating in time, not losing energy doing it. How did this idea even come about? What's the science that lets this happen?
Well, the idea itself was first proposed theoretically
Yeah.
by Nobel laureate Frank Wilczek back in 2012.
Okay, so theory first.
Right. And initially there was quite a bit of skepticism exactly because of that apparent defiance of, standard equilibrium physics.
I can imagine. It sounds like a loophole in the rules.
Kind of, but then experimentalists between 2016 and 2017 actually managed to realize them in the lab.
Whoa, really? What did they use?
They use systems like trapped ions and also things called spin chains, very controlled quantum systems.
So theory to lab reality in just a few years. That feels pretty fast for this kind of physics.
It was remarkably quick, yeah.
So how do they actually make them, or how do they work in the lab? What's the recipe?
It takes very specific ingredients, very specific conditions. You need a periodic external driving force.
Okay, like giving it a regular push.
Think of it like regularly kicking the system, yeah. Maybe with a laser pulse, something like that. But crucially, that's not enough on its own.
Right, because you could just kick a swing, and sure, it'll oscillate for a while, but eventually it stops. Friction, air resistance.
Precisely. So the key differentiator, and the research really emphasizes this, is that time crystals also need many-body quantum entanglement.
Many-body quantum entanglement. Okay, for listeners who follow quantum topics, entanglement is that spooky connection between particles. But why many-body? And why is entanglement needed here?
Yeah, that's where it gets really interesting. So the driving force pumps energy into the system periodically, right?
Yeah.
But the entanglement, that's what links the many individual particles, the ions, the spins, whatever they are.
Yeah.
It links them together in this shared correlated quantum state.
Wow.
And this collective quantum interaction, that's what prevents the system from just thermalizing.
Thermalizing meaning heating up.
Yeah, heating up, spreading that energy around randomly, and settling into equilibrium, like your swing does, because of friction converting motion to heat.
So the entanglement sort of locks the particles together, forces them into a collective dance that resists falling into that random, disordered state.
That's a good way to put it. It forces the system into that non-equilibrium phase we mentioned. But the truly defining property, the absolute signature of a time crystal, is something called its subharmonic response.
The subharmonic response. Okay, the source material really stressed this point. It means the system repeats its state, but not at the same frequency as that external driving pulse, that kick.
Exactly right. You tickle it, let's say, 10 times a second with your laser.
Okay.
But its internal quantum dynamics, which are dictated by that complex interplay of entanglement and the drive, they cause its state to repeat only, say, 5 times a second, or maybe 2.5 times a second, some integer submultiple of the drive frequency.
Ah, okay. So it's not just mirroring the input frequency.
No. That's what makes it different from just a simple forced oscillator, like ringing a bell. A classical system would just vibrate at the same frequency you're driving it at.
But the time crystal imposes its own rhythm.
Its own intrinsic rhythm, yeah, dictated by its quantum properties. That's what makes it a true time crystal, that subharmonic lock.
That distinction feels absolutely key. It's not just reacting, it's creating its own temporal pattern. Okay, right. Let's jump to the really recent breakthroughs you mentioned are in the sources, especially the progress from, 2023 to 2025. This is where it gets really interesting.
Yeah, things have been moving fast. What really stands out in the latest research is progress towards greater stability, finding new experimental platforms, and also developing a more robust theoretical handle on them.
Like that report from May 2025, researchers in China, Shanghai Jiaotong University, observing time crystals in a spin maser. That's a completely different type of system, right?
It is. It expands the family of systems where we know this phenomenon can actually exist, which is important confirmation.
And crucially, back in March 2024, Google's quantum AI team,
Yeah,
they used their Sycamore processor.
that's right. And they demonstrated maintaining these time crystal oscillations for significantly longer durations than had been achieved before.
Keeping that stable repeating state going for longer. That sounds critical if you ever want to, use them for anything practical.
Absolutely. Longevity is key. And then there was the work between 2023 and 2025 by JQI and MIT you mentioned.
What was significant about that?
That's a big step forward on the theory side. They developed a new framework, a mathematical way of thinking about them, that allows time crystals to be treated much like conventional phases of matter.
What does that mean, practically?
Well, before, they were sort of seen as these really exotic, weird outliers, difficult to connect to the rest of physics. Now, this framework lets us use tools we already have for understanding things like, say, solids or magnets, and apply them to simulate and potentially engineer time crystals.
So it's moving from just observing this strange curiosity to potentially being able to design and work with it.
Exactly, moving towards engineering.
Speaking of engineering, this is where the potential applications outlined in the source material really start to shine. What could we actually do with this bizarre phase of matter?
One of the most exciting possibilities highlighted is quantum batteries.
Quantum batteries. Okay, the source makes a pretty bold claim here. Ultra-efficient energy storage. That it says it never loses charge in the traditional sense. Is that right?
That's the theoretical potential, yeah. The research describes lab simulations where these time crystal-like systems maintain their stored energy, essentially their charge, indefinitely,
Oh.
powered by those inherent non-dissipating oscillations we talked about. Unlike, say, a chemical battery that constantly leaks charge over time, or a capacitor that discharges.
Right. Everything runs down.
A time crystal battery, in theory, holds its energy because its fundamental state is stable and just keeps repeating over time without that energy loss pathway.
Wow. So like a persistent energy source derived purely from this temporal periodicity, you could potentially power, delicate quantum sensors or maybe processors without needing constant external power feeds.
That's the idea, providing stable, localized power in a way that might bypass traditional energy loss mechanisms. It's pretty revolutionary if it pans out.
If it pans out, yeah. Okay, and how about quantum computing itself? How could time crystals impact that whole field?
They could be incredibly valuable for stabilizing the quantum states,
Yeah.
the qubits, the things that actually do the calculations.
Okay, why is stabilizing qubits such a big deal? I mean, we know they're fragile,
Exactly. They're notoriously fragile. They suffer badly from something called decoherence.
which is basically losing their quantumness.
Pretty much, yeah.
Right.
Losing their quantum information because they interact with their environment, with heat, vibrations, anything really. And they also suffer from thermalization, just noise from heat messing up their delicate state.
Ah, yeah, the two big nemesis of building practical quantum computers. So time crystals could offer some kind of built-in resistance to those problems.
That's the hope, yes. By their very nature, remember, time crystals resist thermalization. They want to stay in their stable, repeating state over time.
Right. It's their defining feature.
So the idea is, if you could integrate them somehow into quantum processors, maybe they could help qubits hold their information and stay coherent for much longer periods.
Which could lead to...
More reliable and potentially much longer quantum computations than we can currently manage, tackling bigger problems.
Okay, that's huge for computing. But beyond that, the source also points to precision timekeeping. Could these actually replace or improve atomic clocks?
The research suggests they absolutely could. They might lead to the next generation of timekeeping devices, potentially offering accuracy beyond even today's best atomic clocks.
And that's purely because of their defining property again, that incredibly robust inherent repeating pattern in time.
Precisely. They are, in essence, maybe the most stable, naturally occurring oscillators we've ever found, at least at the quantum level. That makes them almost perfect candidates for defining units of time with extreme precision.
And that kind of precision has knock-on effects, right? The source mentioned things like navigation and communication.
It does. Super precise clocks are absolutely fundamental for systems like GPS, for synchronizing everything perfectly. Better clocks mean better positioning.
Okay.
Time crystals could also potentially improve signal stability, maybe making communications more robust, especially in noisy environments. And there are even ideas about applications in things like quantum radar, or maybe ultra-secure communication, where perfect timing is critical.
This isn't just about building better gadgets, though fascinating as that is. The source material also gets into the deeper theoretical implications. How does finding and understanding time crystals actually change our fundamental picture of physics?
Well, it definitely forces us to rethink some core concepts, especially around equilibrium and thermodynamics in these complex quantum systems.
Like the second law of thermodynamics,
Yeah.
the arrow of time, increasing disorder.
Exactly. The standard second law tells us that, systems tend towards increasing disorder, maximum entropy. They lose useful energy, things break down.
The universe runs down.
Right. But time crystals, by maintaining this dynamic, ordered state perpetually without dissipating that driving energy into heat while still being driven. They challenge that conventional picture. At least they show how non-equilibrium systems can behave in ways we didn't fully anticipate over long timescales.
So it's not necessarily breaking the second law, perhaps, but maybe revealing a new regime where the rules apply differently or our understanding needs to be expanded.
I think that's the right way to look at it. It forces us to expand our understanding of these non-equilibrium quantum phases of matter. And the source introduces this really fascinating idea of time crystals being foundational for a whole new class of time-based metamaterials.
Metamaterials. Okay, usually we hear about those for manipulating like light waves or sound waves, right?
Mm.
By structuring materials in space. Think invisibility cloaks and things.
It's exactly. Engineering spatial structure.
So time-based metamaterials would manipulate systems or information in time using this temporal pattern.
That's the analogy, and it's a powerful one. Just like spatial metamaterials, use engineered structures in space to control properties like how light bends or how sound resonates.
Right.
Time-based metamaterials would use engineered temporal structure, that repeating pattern inherent to time crystals, to control how quantum systems evolve or interact over time.
Whoa. What could that let you do?
Potentially, it could allow unprecedented control over quantum dynamics, how energy flows through a system over time, how information processes and sequences unfold. It suggests that time itself at this quantum level isn't just a passive backdrop. It can be structured, engineered.
The ability to engineer things in the temporal dimension, that feels like a genuinely profound shift in thinking.
It really is.
But, okay, this all sounds incredibly advanced, almost still sci-fi. What are the big practical challenges or limitations that need to be overcome to get from these lab sightings to actual widespread applications?
Oh, the source material is very clear. There are significant hurdles. Major ones. First off, stability.
Meaning?
Currently, these time crystals have really only been observed and kept stable under very specific, very extreme conditions. Ultra-cold temperatures, near-perfect vacuum, highly controlled laboratory setups.
Okay, so not something you'll find sitting on a desk anytime soon. Expert speaker.
Not yet, no.
Yeah.
Second major challenge is scalability, making them bigger.
Yeah, it's just very difficult to scale up these incredibly delicate, complex quantum systems much beyond the small numbers of particles demonstrated in labs. Building a large, robust device based on time crystals is a massive engineering challenge.
Makes sense. And the third one you mentioned, integration.
Right. Even if you could make them bigger and more stable outside the lab fridge, how do you actually connect these fundamentally quantum, non-equilibrium systems with the classical computers or even the existing quantum hardware we have? You need entirely new kinds of interfaces, new control mechanisms. That integration piece is really tricky.
So a lot of fundamental science and hard engineering still needed. definitely. We're still in the early days for applications.
Okay, so looking ahead then, based on the source materials outlook for the next few years, say 2025 through 2030, what should we realistically anticipate seeing?
Well, we should definitely expect to see more advanced laboratory prototypes. Things like quantum batteries actually demonstrating some charge holding capability, moving beyond just simulations.
Okay, moving from does the phenomenon exist to can we make it do something even small?
Precisely. And anticipate more work on integration, trying to connect time, crystal principles or components with quantum sensors, maybe even early components within quantum processors.
Still proof of concept stage, probably.
Likely, yes, aiming for potential, maybe limited real-world demonstrations or uses. And the research also points to likely spin-offs.
Spin off.
Yeah, cross-pollination. Ideas and techniques learned from studying time crystals could start influencing other areas. Things like optical computing, advanced metamaterial design, both spatial and temporal, and maybe, as we mentioned, aspects of secure communications. Principles learned here might find application elsewhere sooner.
Interesting. So the core takeaway then, time crystals are not just theory anymore. They are real, a verified phase of matter that actually exists.
Correct. Experimentally confirmed. And the research we've been digging into today really highlights their significant potential to genuinely transform fields like energy storage, computing, precision timekeeping.
Yeah, the list is impressive. But while they are still largely experimental today, the research trajectory seems pretty clear. It suggests that these time-based technologies could really redefine how we harness and even understand both time and energy, maybe within the next decade.
It's certainly a field pushing right at the edge of our understanding of how the universe works at this quantum level. It's
Yeah.
incredibly exciting to watch.
Absolutely. So we've explored how these time crystals exist in this strange non-equilibrium state, repeating in time without, fizzling out, without dissipating energy in the way we expect, seemingly operating outside the usual rules of decay and disorder that govern our everyday experience.
It challenges our intuition about time and energy.
It really does. And it leaves you with a final thought to mull over, doesn't it? Consider this. If we can actually learn to engineer systems that maintain this kind of temporal order, that resist energy loss at the quantum level, what does that ultimately imply about the fundamental nature of time and energy itself? Not just in a controlled lab setting, but maybe, on scales or in regimes we can't even imagine yet.
That's the big question, isn't it? Where could this understanding ultimately lead?